So we've done some problems, and we've got these list of kinds of forces that could be common. Knowing that they're common, then you know you can just go to them to get the formula. Will save you a lot of thinking about how to set these problems up. Now, putting these on a 3x5 card, just like I would the kinematic equations, would be a wonderful idea, and having them someplace in your notes to address these problems would be a great start. Let's describe, though, each of these forces, because I know it's a bit, you've seen them, and you can see that there's some formulas in here. But let's go in and just kind of see a picture of those. So I've listed those forces out. Weight is going to be the first one. The weight is just whatever is pointing downwards from that object, and it arises from the mass. Okay, so weight is always going to be pointed straight downwards. So the weight of this box is straight down. The force perpendicular and force parallel, those are usually for objects on a ramp. Weight doesn't have to be for an object on the ramp, it's just mass times gravity, so that could be anywhere. But these two particularly are for forces of an object on a ramp. That force that pulls it down the slope is the force parallel. You're parallel to the slope of this ramp. The one force that's holding it down here to the surface of this ramp is going to be force perpendicular. The reason that we need to know that first perpendicular is because the board is providing the normal force to keep it from sliding into this area, and that's always going perpendicularly out from the surface that something is sitting on. Okay, it can be on a flat surface or on a ramp like this. Once you know this, though, that's also going to tell you the normal force times some little fraction. Like if it's 0.1, it's saying a tenth of what it would take to lift an object is what it will take to slide an object. A tenth of the force to lift would be what it takes to slide. And so that's the force of friction. It always opposes whatever motion it is. The force of friction is whatever the other force is until it reaches a maximum, and then it doesn't get bigger than what you calculated for. So you can pull on it for 2 pounds, but if the force of friction is 3, the force of friction is only 2 pounds until you get to 3 pounds. Once you get to 3 pounds, then the force of friction stays at 3, and then you can start to move it, and the other one takes over. So those are typical for ramp kinds of problems. Okay, force of friction and weight, they in normal can operate off sides of ramps, but that's fine. A spring normally sits, a force from a spring normally is how much you pull it and how much it'll want to pull back. And so those forces are going to be either in this direction or that direction. So if you pull it, it's going to want to return it to the normal, the stasis position, or if you compress it, it's going to want to return. So your forces for spring are going to be in here. Okay, force of spring. Buoyancy, that's a great one for you guys in Southern California, because you're going to see a lot of these air balloons that are kind of going up. The force of buoyancy is always on this object, and it is going upwards, and the weight is equal, or the size of it is the same size as whatever this volume of air, or the volume of the liquid that you're displacing. So that's the displaced air. If that weighs 1,000 newtons, and you weigh less than 1,000 newtons, then the 1,000 newtons is going to be pushing you up. And if you weigh less than that, then it's actually going to lift you up. If you weigh more than that, you're going to go down, because even that 1,000 newtons doesn't help hold you in the air. It also works on ships, because water is much denser. It'll get a lot more buoyancy from water what your ship is sitting in, and that's what's going to hold the ships up. Force centripetal. Force centripetal is the force that is needed to keep you in a circular path. Like if you're driving down a road and you're taking a corner here, that force is going to be directed towards the center of that circle you're trying to stay on. Torque. Torque is actually, its direction is a little complicated, but I'm just going to say this. It's force perpendicular times the distance to the center of rotation. So if you apply a perpendicular force here, here's your force perpendicular, and then the distance from here to that center is going to become important. If you apply it at some angle, then you're going to have to find the component of the force that is perpendicular. So you may have to do a little bit of component work like we did up there. The last one, force of gravity, is the distance between two bodies that's an attraction. For this moon, for instance, to Saturn. That does equal the masses that you're comparing, the mass of Saturn, the mass of its moons, and dividing it by the radius between them. And then you got to take it times a super small number. Now, if it's poor Sandra Bullock and she's trying to stay attached to the space shuttle, those two masses are so small, there's not much hope for them to come back together gravitationally. When you get to be good-sized planets or suns or those things, then that exerts quite a bit of force. So those are the common forces that we've been dealing with. Hopefully that gives you an idea of what direction they're supposed to be. Centripetal's going in here. The force perpendiculars on a torque has got to be the distance from the center of rotation times that. Gravity is acting between them. Spring is always acting to return it back to its normal size, and then, of course, the four forces that keep a box on a ramp. Perpendicular and parallel are going to become the components of what weight is, and then the force of friction is dependent on the normal. It's some fraction of the normal to keep it from sliding. Hope you have a good time. That's good explanation.